All right, one of the reasons I really love physics is because nothing ever really goes away. It's all tied together. So we have to reference back, even though we're in the uniform circular motion unit, we have to reference back and talk about some really important concepts related to work. And you'll see by the end of the video where we're going, but it might be like, oh, it kind of feels like a couple units ago just for a few minutes here, and then you'll see how we tie it together with the new stuff. So right down the old days, we talked about work. And remember, in order to do work, you had to apply a force, and it had to make the object move a certain delta x. Okay, right? In terms of calculus, the integral of the force function with respect to position, if you take the integral over a certain, from 0 to x or whatever, it'll give you the work. It's an indefinite integral. And so that's work, force and position. Not to be confused for what we just kind of got out of the unit with impulse and momentum. If you ever had a force function that depends on time, and you took the area, that would give you the impulse. So I didn't circle this one because that's not what we're talking about, but I wanted to put them side by side so you could realize, oh, okay, a force function depending on x or position here, and you integrate it, that'll give you the work. A force function depending on time, and you integrate it, that'll give you the impulse, the change in momentum. Remember, if you do work, you can change the energy of a system. If you do impulse, you can change the momentum of a system. So we have that. Let's just look at some examples here. And if you want to have the very basic, kind of simple definition down for work, work equals a force applied times displacement, times the cosine of the angle between those two vectors. And work is a scalar, it's energy, so it's measured in joules. These are vectors, but just to remind this, if you push something to the right and it moves to the right, those two vectors would be lined up. The cosine of 0 would be 1, that'd be maximum work. If you push something to the right, so the delta x is to the right, but the force of friction is going left, then the cosine would be 180 degrees, which is -1, so that kind of makes sense for friction that it's taking energy, or it's doing work by taking energy out of the system. So just make sure the angle here is measured between two vectors you're talking about right there. All right, so that's just a little bit of referencing. We have the very fundamental definition of work. We say, okay, here's the calculus definition. If we integrate the force as a function of position right there, and you can put bounds in your integral. We'll do that in a second here. So we have this right here. Let's just say you have some function, f of x, 6x squared plus 2, and you want to know how much work you do when you move it from 0 meters to 2 meters. So on your AP Physics test, I've never seen a really ridiculous integral or anything like that. You just raise the power, then divide by whatever the power up here became. So it'll be 3 up there divided by 3. That's a constant, so you know it comes from x. So you're like, okay. So we go up, raise it to 3, then we took 6 divided by 3 and got 2. And we said we're going to evaluate it between 0 and 2 meters here. And the 2 just became 2x. And you get that when you move something from 0 to 2 meters for this force function right here, that it's going to cost you 20 joules of energy, just like that. And if you're in calculus, we use newtons and meters, so joules are for energy. They might use foot pounds, or they might use the English units, which would be pound feet. So there we go. Don't let that bother you. It's the same kind of idea. All right. So example 1, just a straight up integral, a force function that depends on. Technically, I should have dx here, right? I'm not a calculus teacher, sometimes I forget my little notation things. So we have that like that, and then you're like, okay, ever like say, hey, EF minus EI equals work. Like maybe there's some outside force doing work. You could take that force, integrate it, find how much work it actually did over that 2 meter interval. So you could say, oh, it started from rest. Now it's moving with some kinetic energy. How fast was it going if you put 20 joules of work in? So you can tie all of these ideas together, but just be ready on the AP test. They could say, hey, all right, find the work. You found it by integration. Now you know the number, and you could figure out, hey, if you got a block that was at rest, boom, 0 joules starts with. And then now here it's moving to the right with some velocity. They could say, hey, how fast is that moving if you did 20 joules of work right there? And you're like, okay, EF minus EI, not equal to 0, it's equal to work, because you're actually putting a force on it to speed that block up. If you didn't put any outside force in there, it wouldn't move, right? And the common misconception is, hey, at the end it's got to have potential energy. No, it only has kinetic because it's moving. Minus, maybe it started with 0 joules of energy just hanging out there, and equals 20 joules. So that's how you get a situation like that. So just have that handy in your brain that you could do some calculus tools with the stuff we did back in the day. All right? That's not the point of our lesson. That's just a callback to what we know. And just to recap this further, you could have a function, you could integrate it to find the work, that's classic, or this function does not represent this graph, it's just totally separate here. They might just give you like a rectangle with a triangle, and instead of making you do like the integral how you know how to do it in calculus. They might just say, hey, you know what? Find how much work is done over this interval from here to here, and you just find the area of the rectangle. Or find out the work done from here to the end, so you'd find the area of the rectangle here plus the area of the triangle. So just be ready for things like that. There's different ways they can ask you for work, either by straight up integrating with respect to position, or by just having a graph and just doing it the good old, we used to call them Riemann sums. You just like that. I don't even think it's that complicated. You're just taking the area of the shapes there. Okay, so we went through that. We did our example, and I don't know why I have this on here again, other than to mention this. If you do 20 joules of work, so I just worked through the same example again. I think this was last year's notes. One thing I want you to keep in mind, it's a super key idea. Whatever your work value is, your change in potential energy is equal to that value, but it's opposite in sign. And if you ever want to keep this in mind, let's say you had a block that was just sitting on the ground right here. And all of a sudden you said, hey, I want to lift up that block. And you know when you lift up that block, to do that, it's going to cost you 20 joules of energy. Because it's heavy, you want to lift it up, it's going to cost you 20 joules. Well, before this block had 0 joules of potential energy, and now it's up here in the air. And it's got some potential energy final. So my argument is, yeah, it had 0 joules of potential energy. Now it has some potential energy final. And what I'm telling you is, if it costs you 20 joules of energy to lift it, that object right there is going to have 20 joules of potential energy at the top. We're assuming we're not losing any energy to heat or anything like that. So when you do work, you can change an object's potential energy. And whatever work you do, that goes into changing that object's potential energy. They're equal in number, but they're opposite in sign. Because picture right here, that cost you 20 joules. Well, it had a positive change in potential energy. It has 20 now when it used to have 0. So 20 minus 0 is 20. So equal in number, opposite in sign. So just keep that in mind as we move forward to the tougher examples, the relationship between work and the change in potential energy. So this is the big ticket. This is the big item right here today. We're going to talk about how this applies to planetary stuff. But before we do, this is tough. So go back and review your work notes. Make sure that what we just talked about makes sense. And then once you're ready, click on video 2. We're going to talk about this planetary stuff right here.